Big data is cursed. We're going to look at two curses: the curse of dimensionality, that data points in high dimensional spaces tend to be very far apart and almost at right angles, and the curse of phantom information. Big data has a huge upside. High volume means that we have data rich, often in applications, lots of useful information, valid results that are very reliable and robust. High variety means there's no limit to what we can call data. Images, video, movie ratings, automobiles, airports, sunglasses, you name it. No limit to how we can mix different data types together. Categorical plus numerical plus video, so on and so forth. So this opens up a whole world to mathematics that used to be limited by the fact that math could really only talk about numbers and geometry to some extent. Now, high variety also means that every big data problem is unique. So when we actually see a big data problem, it's very important that we get up close and personal and figure out what's going on. The black box, just pull an algorithm off the shelf, is not a good approach. There are some downsides to big data. For instance, high velocity. Large data sets can occur so quickly or require algorithms that run so slowly that the results are produced too slowly to be useful. For example, let's look at the subset sum problem. It's a famous NP problem. Given a set S of positive and negative integers, find the largest subset whose sum is 0 if one exists. So, for instance, in this set S we have an example. 1 and negative 1 add up to 0. But negative 1 plus 4 minus 7 plus 19 minus 9 minus 6, that subset also sums to 0. And it turns out it's the largest one. So let's suppose that we wanted to find the largest subset. How would we do it? Well, we just look at all the different subsets. But a set of 250 integers has 2 to the 250th subsets. That means that on the world's most powerful supercomputer, the Oak Ridge National Laboratory's Titan supercomputer, the subset sum problem would require more than 10 to the 51st years to calculate. Why? Because 2 to the 250 power is an extremely large number. And big data is cursed. In a high dimensional space, nearest neighbors, which will remain a very important concept to us, but a nearest neighbor may be very far away. The more space that we have to search, the slower the algorithm. The farther apart, the less reliable the relationship. And also, we'll see that in a complex data set, not all information is meaningful. Let's look, for example, at a hypercube. The observations are adjacent if they differ in only one factor. And so for n equals 2, the n equals 2 hypercube is just a square with vertices at 0, 0, 1, 0, 1, 1, and 0, 1. And the adjacencies are just the edges of the square. The three-dimensional hypercube, n equals 3, is just the vertices of a cube, and the adjacencies are the edges of a cube. Now, what we want to do first is say, what is the maximum number of steps between observations? Now, this is what's called the diameter of the hypercube graph. So what's the most steps that we would have to take in order to go from one point to another in a hypercube? In n equals 2 dimensions, to go from the point 0, 0 to the point 1, 1 requires 2 steps. And this is the farthest distance apart between 2 points, and so we say this has diameter 2. The hypercube has diameter 3 because the 2 points that are farthest apart are 3 steps separated. Also, we're going to say that the line segment from the all zeros tuple to the all ones tuple is the main diagonal of the hypercube. So the main diagonal of a two-dimensional hypercube is just diagonal. Main diagonal of a three-dimensional hypercube goes from the origin out to the point 1, 1, 1. So what is the angle between the main diagonal and one of these x sub j axes? Well, in n equals 2, the angle is 45 degrees. In n equals 3, you have to do a little bit of geometry, but it turns out it's 54.7 degrees. Now what happens as n becomes larger? Well, this angle for n equals 4 is 60 degrees, then 63.4 on up. When we get to n equals 100, it's 84.3, and when we get to n equals 1,000, it's 88.2. So even though this diagonal will never be orthogonal to one of these axes, because it's always going to be the diagonal, the angle between the diagonal and one of the coordinate axes approaches 90 degrees as n becomes arbitrarily large. That the hypercube has that two observations of n factors can be as many as n steps apart. And n here can be very large. So not uncommon for n to be a trillion. So if we have n equals a trillion, then there's a trillion steps between points in the hypercube. Also, this angle, theta sub n, approaches 90 degrees as n becomes very large. What does that mean? That means that big data, which is more complex than the hypercube, can be spread across enormous distances in which observations are approximately uncorrelated. In other words, they all are just about at 90 degrees. This is what's known as the curse of dimensionality. The curse of phantom information we'll explore by thinking of big data as random. Now I put random in quotes here because very often when we study big data we want to use probability theory. Even if the data is not random, we still want to use probability theory. When we think of big data, there will be these patterns, these random-like patterns. They could be the answer, they could be misleading, or they could just simply be there. Now, if you have a sufficiently large and complex data set, then almost any pattern imaginable could pop up. So let's talk about modeling a random process. So first off, we have a sample space of all possible outcomes, and that's sample space is a subset of a universe of possibilities. An event is a subset of the sample space itself. The probability of an event, denoted PR of A, where A is the event, is simply the likelihood that A occurs. Now, events in the universe that are outside of S are said to have a probability of 0 of occurring. Now, let's look at the probability of an event. Suppose we conduct n independent trials of some experiment. We often refer to a random process as an experiment. If A is an event, then we let C sub n of A be the number of occurrences of A in n trials. The probability of A is then the limit as n goes to infinity of the count of the number of times that A occurs in n trials over n. And this is known as relative frequency, the C sub n of A over n. And the limit as n goes to infinity means we need to think of this in terms of n being very, very large. For example, if A is equal to event of heads and we have a fair coin, then the count C sub n of A is approximately 1/2 n as n goes to infinity, because the probability of heads with a fair coin is 1/2. So we're going to look first at probability equal to half. And notice when we have a small number of trials, 10 and now about 20, that the relative frequency is not close to the 0.5. So saying that 0.5 is a probability means that we're letting n go to infinity, and as n becomes large, you can see that the relative frequency of heads with respect to the number of trials is approaching 1/2 for our fair coin here. The same thing happens if we look at, say, probability of heads being 0.25. And by that I mean when n is small, the number of trials is small, then it's not close to 0.25. But as the number of trials increases, the relative frequency for probability of heads being a fourth, the relative frequency approaches a fourth. And as n becomes very large, it becomes closer and closer to a fourth. Even when we have a probability of 0.05, now it takes a long time before we see the first heads, because 0.05 is about 1 in 20. So we expect 20 or so coin tosses before we even see the first heads. But once we see the first heads, then once again, as the number of trials becomes large, the relative frequencies approach the 0.05. This is what's known as the law of large numbers. As the number of independent trials of a process increases, the averages over the measures of the trials of the trial data approach theoretical expectations, where the theoretical expectations are from mathematical models of the process itself. So relative frequencies approach a theoretical probability, and notice they often do this after only a few thousand trials. We never got more than about 250,000 trials in these simulations. Many independent trials implies many independently identically distributed variables x sub I, and many patterns emerge. For example, if we have 20 consecutive coin tosses where we have tails and then 18 heads and then a tails, with a fair coin, we would expect practically a probability of 0 of a tails, 18 heads, and a tails in 100 coin tosses. But in 1,000,000 coin tosses, it's almost a probability 1 that we will see this pattern. If we happen to focus on this single run of 20 tosses to make a prediction, our prediction would be wrong. The larger the data, the more patterns that can occur, and big data tends to involve extraordinarily large numbers of data points. Moreover, big data fights the law and wins. Events with probability 0 can and do occur in big data sets. Let's look at an example. Suppose we're given a coin, and this coin has the property that it balances on its edge no more than once in 1,000 coin tosses, no more than twice in 4,000 coin tosses, and no more than 3 times in 9,000, and no more than n times in 1,000 n squared tosses. So this means our count is n when the number of trials is 1,000 n squared. So the probability that this coin balances on edge is less than or equal to n over 1,000 n squared as n goes to infinity, but clearly that's equal to 0. If we had actual data, then we would mark balancing on edge as NA or not available. In other words, we just can't get a heads or a tails if the coin balances on edge. So even though the probability of missing data is 0, we have not ruled out seeing as many as 100 balances on edge outcomes. In fact, up to 10% of the observations could contain trials where a heads-tails outcome is not available, even though the probability of not available is equal to 0. So in big data, there's many patterns and there tends to be missing data. We should expect a high volume and high variety of patterns when working with big data. Typically, our goal will be to find relatively small collections of informative patterns within a huge amount of non-informative, random-like data. And big data tends to be so large that we should expect things that should be impossible, like missing data, to occur quite often. So what is big data? Large amounts of data, high volume, complexity and high dimensionality, high variety, and data is produced faster than standard methods can analyze it, high velocity. But the curse means that the information we want may be difficult to obtain, and that the information we obtain may not be meaningful.